Okay, we're going to look at some examples with linear systems. I'm not going to go through and do all the operations like we did in the previous example, and I'm just going to skip to the main thing. But we're going to also define something extremely important called the reduced echelon form of a system. And the idea is this. Suppose I've got a system of equations. So I've got A is a matrix, X is a vector of my unknowns, and B is a vector of constant values. All right, so in this case, let's say, for example, that I have 5 unknowns. And I can write this as an equation where I've got 5 columns, and let's just assume we have 5 rows. That's not always the case. But let's suppose we have 5 rows, and then I'm going to have 5 values there. So I got constant numbers, and now first thing I would do is I would choose this for my pivot, and I would go down that first column and make all zeros there. Then I would choose this for my next pivot and make zeros underneath that. And then after I've done that, this would be my next pivot, and I would go down that way. Now, if I got to here and there were all zeros here, then I would basically have to skip and then use that as my pivot. And sometimes that happens. Let's just pretend I go through and I do everything, and after I'm done, my system is in this form. This is for my augmented matrix. So I do all the operations like we discussed in the previous video. I can be careful. So I've got to have 5 rows. And the reason I have to have 5 rows is because I said earlier that I had 5 equations. I could have 4 or 3 or 8 equations. It's just that in this particular case, I said I'm going to have 5 equations. So if I have 5 equations, I need to have 5 rows. Let's suppose that I go through and I do everything and I get down to here. What is important? What is important here is if I go to any row and I find the leading thing that's not 0. So row 1, this is the first entry that's not 0. Row 2, that's the first entry that's not 0. And row 3, that's the first entry that's not 0. And then everywhere else, the following rows are all zeros. Right, so these were my pivots when I did my operations. Note in each thing I have a 1 in each pivot. Okay, that's going to be important. So if that's the case, and I've got all zeros here, and now the other thing that's important is that for each pivot, I have zeros below and above each pivot. Okay. And again, I have zeros below where all my pivots occur after that. Okay. Okay. If this is the case, if I can get my matrix in this form, we're going to say it's in reduced row echelon form. Okay. And don't want to write that out all the time, so I'm going to call it RREF. And so there's a couple key things here. Is any row with all zeros is at the bottom. All right, so I've got rows with all zeros there at the very bottom. Um, let's see, for each row, the first non-zero entry is a 1. And we're going to call that the pivot for that row. And for each pivot, there are zeros above and below. All right, so for each of these pivots, if I look at the rows above and the rows below, I have zeros everywhere. Okay. If all of these things are true, then we will say the matrix is in reduced row echelon form. And why is that important is that if I have something in reduced row echelon form, I can tell you about the solution. So we said that the reduced row echelon form for this, so the idea is I can put this in an augmented matrix, and after it's in reduced row echelon form, let's just suppose I got this equation, or this system of equations, like so. And because of the way we defined the augmented matrix, I know this is my matrix A, and I know I'm going to multiply it by x. So each column are the coefficients for my unknown variables. In this case, I said they were x1, x2, x3, x4, x5. And then each row represents an equation for those variables. And what does this mean? I can just immediately read this off. The first row says that x1 plus 2x3 equals 2. Second row says x2 minus x3 plus x5 is 3. And then the third row says that x4 plus 2x5 is 3. I think on the previous page I had a 1 there. Yeah, I did. Let's just go with this to make this less confusing. Let's just suppose this is what I had. Now, x1 represents a pivot variable, x2 represents a pivot variable, and x4 represents a pivot variable. So I can solve these things in terms of these other variables, and these other variables are not pivot variables. So equation 1 says that x1 is 2 minus 2x3. Equation 2 says that x2 is 3 plus x3 minus x5. And equation 3 says that x4 is equal to 3 minus 2x5. So here's the thing, is my solution depends on x1, x2, x3, x4, and x5. I know that x1 depends on x3 and x5. In this case, it's 2 minus 2x3. x2 I know depends on x3 and x5. Notice there's x3, there's no real restriction on there. Nothing says anything about what that should be. And then x4 is 3 minus 2x5. And x5, like x3, has no restriction on it. So this means that x depends on x3 and x5. So if you give me any numbers or any values for x3 and x5, that automatically determines what x1, x2, and x4 have to be. And that's going to be, so there's going to be a 2 in the first row, 3 in the first row, 0 here, 3 from here, and a 0. And the coefficients on x3 are going to be minus 2 1, 1, 0, 0. There's no x3s here. Now it's for x5. There's no x5s there. There's a minus 1 x5. There's no x5 there. There's a minus 2, and there's 1 x5 there. So my solutions to this system of equations is given by this. And you can give me any values for x3 and x5. And as long as I use those to calculate x1, x2, and x4, I'm going to have a solution to the original equation. And notice this implies that I have infinite solutions. Okay. It's going to turn out later when we look at this, I can think of this as my particular solution. If I plug this in for x, I'm going to get equal to b. If I plug this in and this in, these are essentially going to be homogeneous solutions. If I put that in for x, I'll get ax equals 0. And basically I'll get ax, a times this will give me b, a times x will give me this as 0, a times this will give me 0, and I'll basically just get the b. Okay. All right, let's look at another example. Suppose I have x minus 2y plus 4z is minus 5. 3x plus y plus 5z is 13. 4x plus 2y plus 6z is 20. If I put this in an augmented matrix, first equation is 1x minus 2y plus 4z is minus 5. Second equation is 3x plus 1y plus 5z is 13. Third equation is 4x plus 2y plus 6z is 20. Okay. Let's do this. So I'm just going to go through and put this in reduced row echelon form. It's going to be my first pivot. So I'm going to leave that row alone. It's already a 1. So I want to take row 2 minus something times row 1. So if I take 3 minus that, I'll get 3 minus 3 is 0. I'll get 1 minus a minus 2 times 3 is 7. I'll get 5 minus 12 is minus 7. Then I'll get, 13 plus 15 is going to be 28. And now, so I got to put a 0 there. I want to get a 0 there. So I want to take my row 3 and subtract something times row 1. Well, I'm going to just take minus 4 times row 1. That'll give me a 0 there. So I'll get 2 minus a minus 8 is 10. Is that correct? Yep. And I'll get 6 minus 4 times 4 is going to give me minus 10. And then, is that correct? Yeah. I'm going to have 20 minus minus 4 times 5 should give me 20 plus 20 is 40. Okay. All right, so now I'm going to move to this. So that takes care of my x. This is my next pivot. So I'm going to leave the top row alone. I want to get a 1 there because that's my pivot. So I'm going to do 1/7 of row 2. So minus 7 divided by 7, 28 divided by 7 is 4. And now I'm going to leave everything else alone. Sorry, this was my pivot. This is my pivot. So I'm going to go down to get a 0 underneath. So I'm going to leave the next 2 rows alone. So I know that when I'm done, I'm going to get a 0 there. So how do I do that? I'm going to take my third row, I'm going to subtract. So this is my pivot is row 2 now. So if I just take 10 times row 2, I should get a 0. So this is going to be minus 10 minus a minus 10 is 0. Then 40 minus 4 times 10 is 0. Now I'm going to go down to the third row. Notice everything is a 0, so there's no pivots there, so I can't do anything. This is a pivot, this is a pivot. This is not in reduced row echelon form, because if I look at each pivot, I have something that's not 0 above one of the pivots. So I need to make a 0 there in order to get this in reduced row echelon form. So I'm going to leave the bottom row alone. I'm going to leave the middle row alone. And I know that when I'm done, I'm going to get a 0 there. So I'm going to take my row 1, and I'm using this now as my pivot, so I'm going to subtract something times R2. And if I'm going to need a minus 2 times that. So let's see, so this is going to give me 1 minus 0 times 2 is 1. Minus 2 plus 2 is 0. And this will give me 4 minus 2 is 2. This can give me minus 5 plus 2 times 4 is 8, so that's going to give me 3. Is that correct? I think so, yeah. All right, so now this is a pivot, this is a pivot. I've got zeros above and below, no pivots in column 3. Bottom row is all zeros. So now this is in reduced row echelon form. Okay, and now I can try to figure out the solutions to this. So what does it say? The first row, and keep in mind the columns are the coefficients on my variables. Oops, sorry, I started off with x, y, and z, so I gotta stay true to that. First row says that x plus 2z equals 3. Second row says y minus z is 4. X is a pivot in the first row, y is a pivot in the second row. So I'm going to solve for those. So x is 3 minus 2z, y is 4 plus z. So my solution looks like x, y, z. X is 3 minus 2z, y is 4 plus z. Z is not a pivot, so I can't do anything with that. So if I break this out into the constant terms, and then the z's, I'm going to have a minus 2, 1, and 1 for the coefficients. My solutions to this system of equations are going to look like this. And that's going to be true for any value of z. You give me any value of z, that's going to define x and y, and it's going to solve this system of equations. And notice I have infinite solutions. Okay. Let's look at an example here. In this example, I'm just going to tell you what the reduced row echelon form for the system is. Suppose I give you ax equals b. And what normally happens in practice is you just plug into MATLAB the augmented matrix and you tell it to do the reduced row echelon form. Suppose it spits out the following. So the first row is 1, 0, 0, 7, 0, and then a minus 3 for the b. Second row is 0, 0, 1, minus 2, 0, 1. Third row is 0, 0, 0, 0, 1. That equals 2. And then the fourth and fifth rows are all zeros. If I give you this on a quiz or test, you should be able to react to this and figure out what this means. You should immediately look at this and say, okay, there's 5 rows. That means there was 5 equations or 5 rows in the original matrix. There's 1, 2, 3, 4. There's 5 columns, which means there was 5 columns in the matrix, in the original matrix. And each column represents the coefficients for the unknowns. So there's 5 unknowns because there's 5 columns. You should recognize that x1 has a pivot, x3 is a pivot, and x5 is a pivot. And x3, x4 could be any value, and those are going to define what x2 and x4 could be any values. And if you give me any value for x2 and x4, that will define x1, x3, and x5 because those are pivots. Okay. So in terms of finding the solutions now, I'm going to go row by row. Row 1 says that x1 plus 7x4 is minus 3. Row 2 says that x3 minus 2x4 is 1. And then row 3 is x5 equals 2. So that says for my solution, my state is x1, x2, x3, x4, x5. Solving for the pivot variables, I get that x1 is minus 3 minus 7x4. x2, well, there's nothing in there that tells me anything about x2, so x2 is just x2. x3 is a pivot variable, so I know that x3 is 1 plus 2x4. x4 is not a pivot, so there's nothing I can do with that. But x5 is a pivot, so I just know that x5 equals 2. So breaking this out into my constants, so in this case I only have one free variable, x4. So I get minus 3 from the first, 0 from the second, 1 from the third row, 0 from the fourth row, and then 2 from the fifth row. And the coefficients on x4 are going to be minus 7. Oops, I got to be careful. I forgot the x2. We'll come back for that. There's no coefficient on x4 in this equation. In this equation, there's a 2x4. Coefficient on this equation is 1, and there's none in that. And then finally for x2, there's none there. There's 1 in the second row, and there's not any, so 1, 2, 3, 4, 5, in any of the others. So for any, you give me any values for x2 and x4, that defines x1, x2, x3, x4, and x5 using this expression. And these are going to be, I'm going to have infinite solutions to my original equation, and this is what they're going to look like. All right, one last example. I'm just going to state the equation and state the reduced row echelon form rather than go through everything. Suppose I have x plus y is minus 2, minus 3x, minus 3y plus z is 9, then x plus y plus z is 2. When I put this into my augmented matrix, so I'm going to have 3 rows, I'm going to have 3 columns because I have x, y, and z. It's going to be 1, 1, 0 equals minus 2. Second equation is minus 3x minus 3y plus z is 9. And the third equation is x plus y plus z is 2. So there's my augmented matrix. At this point, you should be able to reduce this and put it in reduced row echelon form. If you do that, you should get the following. 1, 1, 0, minus 2, 0, 0, 1, 3, and 0, 0, 0, 1. Now, the question is, how do you interpret this? So, again, there's 3 columns, so we know that we have 3 unknowns, x, y, and z. We have 3 rows, which means we started off with 3 equations. This first row says that x plus y is minus 2. Second row says z equals 3. And the third row says 0 equals 1. This is saying then, because we have all zeros here and not 0 there, that means then that my original system was not consistent. There's no way for me to satisfy all 3 of those equations, which means then that there's no solution.